All right, here we go. So today's our last lesson on vectors. Today we're going to learn about how to subtract vectors. So the objectives are basically the same as they were for addition. You need to make sure you understand that subtracting vectors is not the same as subtracting scalars. Here's the one that's probably new. You need to make sure that you understand how to draw subtraction problems. And the most common way of doing that is to draw the subtraction problem as addition. All right. And then ultimately your major goal is to be able to use vector components to subtract vectors, just like last time. So here is the deal. Just like in algebra, subtraction is the same thing as adding a negative. All right. So here's what I mean by that. So in algebra, one of the things that you learned how to do very early on was something like this. You'd be given a problem where it said, oh, well, x plus 5 is 8, and you'd have to find out what x was, right? So to do that, you'd rewrite this as a subtraction problem. You'd subtract 5 from both sides, and you'd get that, oh, well, that's the same thing as saying x is 8 minus 5, right? So now I have a subtraction problem. So our vector subtraction problems are going to be presented like this, where you're given, you'll know what the total is, and you'll be missing some unknown thing that contributes to that total. Okay? So we'll rewrite that as subtraction, but then, to go one extra step further, in math class, you're often taught to rewrite subtraction as adding a negative. So this then becomes x equals 8 plus negative 5, right? Okay? So we're going to be looking at vector problems that are like presented this way, where you're missing some unknown at the beginning, and we're going to rewrite it as adding a negative. Okay? So here is an example of that. All right, so here we go. Roy's house is at the corner of Ash and Cedar Streets. All right, so Roy's going to walk from his house 3 miles up Ash Street. So let's call that vector A. Vector A is going to be his walk up Ash Street. And he's going to go 3 miles up Ash Street, which runs at 30 degrees north of east. Okay? Then he's going to turn and he's going to walk on Briar Lane. And he walks along another straight path, but it doesn't tell us how far he went. So, or even what direction he went. So vector B is this sort of unknown quantity, okay? And it kind of maps up with x in this example over here, right? This is the thing we don't know, okay? Now, his friend Sally walks up Cedar Avenue. Cedar Avenue. She goes 4 miles at 20 degrees west of north. So let's call vector C Sally's walk. She's going to go 4 miles up Cedar Street, which runs at 20 degrees west of north. Okay? And she ends up at the same spot as Roy. So this ends up at the same spot as Roy is a fancy way of telling us that this thing here is the resultant. Okay? So why is that true? Well, let me see if I can explain why that's true. So I'm going to go over here. Let me clear up a little space. All right, so in the last video, we learned how to add vectors, right? So I'm not going to use A, B, and C again. So let's use, I don't know, how about P, Q, and R? All right, so here's vector P. Okay? And here's vector Q. Okay, so if we wanted to mathematically add vectors P and Q, what we'd have to do is we'd have to take either vector Q and place it at the head of P, or vice versa. Let's just take Q and we'll move it over to here. Whoops, that was weird. Okay, so there I now have placed vector P and Q head to tail, and so my resultant is this, right? Here's my resultant. So this is the same as P plus Q, right? Well, notice that this resultant vector goes from the place where vector P originated and ends at the place where vector Q ends, right? So it's as if we went in a straight line from our initial sort of point to our ending point, right? And that's exactly what Sally did, right? Roy walked down 2 paths. Roy walked down, oh, this drawing is actually, oh, not at all accurate. Never mind. Okay, so Roy walked down 2 paths, and then Sally walked in 1 straight path to get to the same spot. Okay, so that is that. I've also just realized I'm unhappy with my colors over here, but whatever. Most of you are probably not keeping up with that. Okay, so, So how do we solve this? We got to figure out what vector b is that's going to get us to that resultant vector. All right, so there are two ways, there are two ways to think about this. So the first way would be graphically. Okay, so let's do this. Let's draw vector A. So vector A is 3 miles at 30 degrees north of east. So here's my little compass. So northeast, 30 degrees north of east is going to be kind of this way. All right, so we'll mark that off, 3 miles. So there's my vector A. Now I don't know what vector B is, right? So it's going to, don't draw this, I would just listen at this point. But vector B is going to, you know, kind of point off in some direction. We don't know what direction or how far. But what I do know is that that vector has to end at the same position as vector C. So let's draw vector C. All right, so let's see. Vector C is 4 miles at 20 degrees west of north. Got it. Yeah. So let's see. So here's where I'm going to start my vector C. Remember, it needs to start at the same spot. And it's got to be 20 degrees west of north. And it's got to be 4 miles. 1, 2, 3, 4. What did I do? 1, 2, 3, 4. Something like this, right? So there's my vector C. Well, that now tells me what vector B must have been. Because vector B is the vector that, let me erase all these green dudes now. So vector B is the vector that gets me from the end of A to the same place that Sally walked to. So there's my vector B. That's the vector I'm looking for. Okay? So this drawing here is a drawing of A plus B equals C. All right? But so here's the deal. We need to find vector B. So let's solve this thing for B. All right? So if I do that, what I get is this. I get B equals C minus A, which is the same as saying plus negative A. All right? So negative A is exactly what you'd think it is, right? Vector A was this. We walked 3 miles this way, right? So negative A is walking 3 miles in the opposite direction. Okay? So think about this then. So if I want to find B, what I'm going to do is I'm going to take C and add the opposite of A. All right? So look, let's draw this. So here's my vector C. So I want to start here, and I want to go 20 degrees north of west for 4 miles. So 1, 2, 3, 4. So hopefully that vector there looks about the same as my other vector C. So here's my vector C. Oops, there's a terrible letter C. Here's my vector C. All right, and now I want to add negative A. So give myself some room here. Okay, so here's my vector C, and now my goal is I want to add negative A, right? So negative A is this dude. So it's, let's see, so I'm going to go here, and I'm going to do negative A. Something like that, right? 1, 2, 3 miles, right? So here's negative A. Okay, so let's see. Right now I've got exactly what I wanted, right? C plus negative A. And that ought to be vector B. Oops, that's a terrible arrow. All right, and so what do you notice? Well, look, this vector B here looks pretty much the same as this vector B here, right? Okay. All right, and then the other thing you can think about too is that when you add vectors, the order doesn't matter. So I could have written this as negative A plus C, which actually is going to look exactly the same as my first drawing, right? So I'm going to start here. Here's negative A plus C. Ding, 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 ding. I don't know why I said ding there, but so that's the deal. All right, so you need to be able to kind of manipulate these equations a little bit to make your drawings look meaningful, I guess. Okay. All right, now, so finally, doing that graphically isn't very helpful, right? So how do we do it mathematically? All right, well, here's the deal. I have some notes written here somewhere so that I don't, no, here we go. Okay, so So the process is the same as before. You take your vectors and split them up into components, all right? So here are my vectors. My vector A is 3 miles at 30 degrees north of east. You guys all know by now how to draw the triangles and find the components. So it turns out that the x component of A here turns out to be 2.598. And the y component turns out to be 1.5, okay? Now I can't do anything with vector B because I don't know what it is, but I can do vector C, right? So vector C ends up having an x component of negative 1.368 and a y component of 3.759, right? And what am I missing? Well, I'm missing bx and by, right? So this column here gives me this equation. Let's see, 2.598 plus bx equals negative 1.368. So subtract 2.598 from both sides, and you'll figure out that bx is negative 3.966. Okay. This over here gives me this equation. 1.5 plus by has got to be 3.759. So again, subtract 1.5, and you find out that by is 2.259. Oh, right on. Now I can, no, I'm almost done, right? So let's see, bx has got to be negative, so let's draw that. So here's my bx, negative 3.966. Oh, darn it. My by is positive, so here's my by. By is 2.259, and now I can find my vector b, which looks pretty similar to my vector b. Not perfect, but not too bad. So what this black triangle is this triangle here. Here's my bx, and here's my by. Okay? So we can find vector b now. We know the x component and the y component, so we can find vector b, right, just by doing a little bit of trig. So Pythagorean theorem tells me the hypotenuse, my vector b, is 4.564, which I'll just round to 4.6 miles. At a little bit of trig here tells me that that angle is pretty close to 30 degrees. It's like 29.7 degrees, and it looks like it's north of west. Okay? So that's that. All right, so you're basically just sort of solving for an unknown, and you'll notice that these problems, even though they're technically subtraction, right, because what we just did here was c minus a, right, but we still wrote them as addition problems, okay? All right, so what I would like you to do is try one on your own. So again, I gave you a velocity one. The fact that it's velocity doesn't change anything, okay? You've got a river flowing. You've got a boat crossing the flowing river, and so the question is, how fast would the boat be going if the water wasn't flowing? Okay? So, there you go.